section 5.2 is on perpendicular and angle bisectors. So we actually have already used these terms before, so I think you guys know what these mean. So what a perpendicular bisector is it's a segment or line or whatever that divides a segment into two equal pieces, and it's also perpendicular to that segment. Okay, so there's going to be two things that we're going to draw. So every time we have a perpendicular bisector, we have a 90-degree angle, and these two pieces are the same. So think about the words in perpendicular bisector. Perpendicular bisector cuts the segment into two equal pieces, right? So the converse, so it says, if a point is on the perpendicular bisector of a segment, then it ends up being equidistant from the endpoints of the segment. So any point along this perpendicular bisector, so if I pick this point right here, everybody see the point I just picked? Do you think it's the same distance from A that it is from B? Yeah, it is. So if I draw on these lines, connecting A and connecting B, these two are equal. Okay, think about why that's true based on that last chapter that we just did. Could we call those two triangles congruent to each other? Do they exactly match up if I fold it over? Yeah, they would be congruent by side, angle, side. Because we have the reflexive property creating that side in the middle, right? That's the same. So those two triangles would be congruent by side, angle, side. Therefore, all of their corresponding pieces would be congruent. What do we use when we were trying to prove that? CPCTC, exactly. Oh, good. You guys remembered past Thanksgiving. Good. All right, so the converse of the perpendicular bisector theorem says, well, if these two sides are congruent, then if I fold across this line that I'm creating in red is what we call a perpendicular bisector. So it creates a perpendicular angle, and these two segments are congruent. Okay, so it works in both directions. So for example number 1, we have this picture here, and we know that these two segments are congruent down there. So if those two segments are congruent, imagine taking a piece of patty paper and folding it over on itself. Can you guys all visualize this? It's never really a hard one for my geometry students to visualize. Those two blue lines are going to be congruent to each other. Okay, so we're going to have here and here. So we're going to say 3x plus 9 has to equal 7x minus 17. So I get 4x, and then I add the 17 over, so I get 26. So I get 13 over 2, or 6.5 would be the answer. All right, so this one tells us stuff. It says if xw is congruent to zw, so if these are the same, and the measure of xwy is 5x minus 19, so xyw, so this angle right here is 5x minus 19. I'm going to put it in parentheses and put a little degree there. And the measure of zyw is 3x plus 3.4. Find the values of both x and y. Yeah?
For number 1, wouldn't it be 36 times 26?
Is it 36? I think it's 26 because you're going to add the 17 over. 17 plus 9.
Add the 17 to 9.
Uh-huh. So I think that should be 26, right? Because like 17 plus 10 would be 27.
Oh, wait, no, I'm sorry.
You're thinking like 19 and 17. That's all right. It's a struggle. The Monday after Thanksgiving, man. You're just dreaming about cherry pie and pumpkin pie. I know. It's hard. It's like summer break all over again. All right, so here we go. So what are we going to do? So what's the first equation we can set up? Yeah, so how do you know that those angles are going to be congruent to each other? Yeah, because you can say those two triangles are congruent to each other. You end up getting it by CPCTC, basically. You get the two triangles are congruent to each other by side, angle, side, and then by CPCTC, geez, these two are equal to each other. So we're going to say 5x minus 19 equals 3x plus 3.4. So we start subtracting over, we get 2x. We add the 19 over, so we get 22.4. And then we divide by 2, so I think we get 11.2. I'm going to move you to the front. All right, the next one. So we're finding y. So what's an equation that finds y? Yeah. 5y minus 1 equals y squared minus 1. Now in this case, I can add 1 to both sides. I get 5y equals y squared. Now this is a tricky one because we've had y squared equations and we always factor. And in this case, we're actually going to factor as well. We're going to get everything on one side and we're going to set it equal to 0 just like normal. So we're going to have y squared minus 5y. And there are two solutions that are going to make that true. Okay, it's not like our typical factoring. You guys remember the ones where we had like plus 6 and then we would factor this way? We don't have anything that's like plus 6 on the end, right? Anybody remember how to factor this from Algebra 1? Yeah, what would you do?
Oh, don't you take the y out?
Yeah, exactly. So we pull out the y. When we do, we have y times y minus 5. So we get both y equals 0 and we get y equals 5. Okay, and then think about it. So sometimes both of those answers work. I think I had one like this on your test where actually there was more than one thing that works. That can happen. So if I plug in 0, are both of these equal to each other? They're equal to each other, but what is it? They're both -1. Can I have -1 for a length?
No.
No. So 0 actually doesn't work because I'd have lengths of -1. But 5 works. If I plug 5 in, I get 25 minus 1, which is 24. So 24 equals 24, right? So that's it. All right, it's not always drawn to scale, too. So if you had other side lengths and you were like, wait, that one's longer, but it looks shorter, that's okay. All right, so this one says find the two possible values for x. So again, we have the same kind of picture, and we're going to say that 3x squared minus 2x plus 5 equals 2x squared plus x plus 3. And we're going to try to factor. We're going to get everything on one side. So subtract the 2x squared over, so I get x squared. I subtract my x over, I get negative 3x. I subtract my 3 over, I get positive 2 equals 0. And go ahead and try to factor. So when we factor, we get x minus 2 and x minus 1. So my answers then are x equals 2 and x equals 1. And you can do a quick check. Both of those give you positive segment lengths. So both of those actually do work. Making sense so far? Easy enough? There is something hard in Chapter 5, but I'm going to end up giving you a little note card to help you because it's the next section. All right, so angle bisector theorem. These ones are not hard either. So what do we know about an angle bisector? We know that an angle bisector bisects an angle. It breaks it into two congruent pieces. So it says if a point is on the bisector of an angle. So do you guys see this right here? This point D is on the bisector of the angle. It ends up being an equal distance from the sides of the angle. So this is not the distance to that side. Do you guys see that blue line I drew in? I never say, oh, if I try to draw it to the side of the angle. That's not the distance. The distance to a side is always perpendicular. So if this is my point, the distance to the sides of the angle, so these are the sides of the angle, ends up being these perpendicular lines. Okay? Those are the two distances that are going to be congruent to each other. So this distance ends up being the same as that distance. Okay? And surprise, the converse of this one actually works as well. So these could be stated as if and only if statements. Right? Do you guys remember a biconditional from Chapter 2? Do you guys know what I mean by if and only if? You got to start knowing this stuff because it's going to be on your final, right, in 3 weeks. You remember all this? So the converse of the angle bisector theorem says, well, if we have two pieces that are congruent right there, then this line has to be the angle bisector. Okay? Again, what I think of is literally patty paper. I think about that in my head. I'm like, if these were on patty paper and I folded them on top of each other, what would be true? Do you guys see that when you think about patty paper? Yeah. All right, so the first example says find x, jk, jm, and kl round to 3 decimal places if necessary. So what do we know? So we know that we have an angle bisector. So when we have an angle bisector, this segment and this segment are congruent to each other. So we know that x plus 5 has to equal 2x minus 7. So that means that x has to be 12. So if I'm finding all these different things, I know x is equal to 12, and then I'm asked to find jk, jm, and kl. So what's jk? What length is that? Yeah, x plus 5, so 12 plus 5 is 17. Same with JM. It should be 17, is it? 2 times 12 is 24, minus 7 is 17. KL? Ooh, we don't know that one. Ah, how'd you get it, Koki? You're right. Oh, let's see. Okay, let's look at it. So we have this little right triangle. Oh, I'm just clicking on everything. Let's look at this little right triangle right here. We knew this side was 17. And we knew that JL, the hypotenuse, was 12 plus 17 was 19. How do we find this distance here, which I'll call y? Yeah, we do our a squared plus b squared equals c squared, Pythagorean theorem, right? So we're going to do 17 squared plus y squared equals 19 squared. 19 squared is 361. 17 squared, anybody know that? No one. 289. And then we subtract over. So we do 361 minus 289. And we get y squared equals 72. So that's what Koki's saying. He's saying y squared is 72. So now we take the square root.
So we have more easier way to calculate.
Oh, you do?
Squared minus 17 squared is 90 plus 70 times 90 minus 17.
Oh, you do it that way?
So it's 36 times 2. So it's 72.
Wow. You have to show me that after class. That's cool. So it's a quicker way of doing it that you learned in school when you were younger?
It's algebra.
You did what now? So you did 17?
19 plus 17 and times 90 minus 17.
Times 19 minus 17? Oh, it's like, I see what you're doing.
Yeah.
So you're saying like x squared minus y squared, it factors into x plus y and x minus y? Yeah, so you get there faster?
Yeah.
Cool. Interesting. All right, so the square root of 72 then is going to be like 6 root 2. So y is going to be 6 root 2. So that's going to be our distance for KL. So 6 root 2. Make sense? All right, and the very last example, what do you think we do on this one? It's pretty easy. 5x minus 2 equals 3x plus 14. And we know we can do that because these distances were equal. So again, imagine you have that patty paper and you're putting those triangles directly on top of each other. Does it make sense that they're matching up? Yeah, because we have the reflexive property here. We had these two were congruent, and then we had the 90-degree angles as well. So because of that, we have hypotenuse leg. Okay, so we can say those two triangles are the same. So we end up getting, subtract the 3x over, we have 2x. Add the 2 over, we get 16, so I think we get x equals 8. So all that stuff we learned in the last chapter comes into play in this chapter because we can quickly get these theorems from those things. Okay? Is that the last one? All right, so now you guys can do the